Okay, so LP20. Okay, let's see here. So we've got a line L, and we've got an X naught, and we've got a V, and then we've got some point X that's not on L. So let's draw our picture. It's getting complicated here. So here's L, and we've got this vector V parallel, and we've got this point X naught that's on the line, and then we've got some other point over here X that's not on the line. Okay. Okay. Now let me scroll down here just a touch. Oops. Okay, so let P be the point on L that is closest to X. All right, so there's going to be some point over here. And, of course, this is going to be perpendicular if that's the closest point. And that's our point P. Okay. We want to show that N1, namely that cross product, is perpendicular to both V and X minus P. So, by the way, X minus P is this vector. And let's see. Okay, right. Okay, so now what I know is that this N1 vector, that cross product, is clearly perpendicular to V and X minus X naught, because it's the cross product of those two things. All right, so in fact, let's see here, X minus X naught is this vector. So this N1 is kind of, it's sitting up here like that, and it's perpendicular to the line, and it's also perpendicular to that. So geometrically speaking, I claim that in being perpendicular to the line and in being perpendicular to this vector, it's sort of perpendicular to the whole plane that this problem is happening in. And so, well, X minus P is parallel to that plane, and this is perpendicular to that plane. So, I mean, geometrically, it's kind of appealing. But let's write down the algebra, because what I know is I know that N1 dot V is equal to 0. I also know that N1 dot X minus X naught is equal to 0. And I claim that, note that X minus P, this X minus P is going to equal to X minus X naught plus some multiple of V. And I don't know what that K is exactly, but there's going to be some multiple of V that I can add to this vector to get me to that vector. Does that make sense? You sure? Okay, well, let me say that differently then. Note that, okay, how about this? P minus X naught, this vector here, that's equal to KV, for sure, right? Because it's P minus X naught is parallel to the line. And then, so X minus P is going to equal to X minus X naught plus X naught minus P. And X naught minus P is the negative of that. So, okay, so this is the minus sign. Is that cool? Yeah, okay, cool. All right. Okay. So let's compute now what is N1 dot X minus P. Well, that's going to be, by this algebra, it's N1 dot X minus X naught plus KV, and I know that N1 dot X minus X naught is 0, and I know that N1 dot KV, or N1 dot V is also 0, and therefore this dot product, when I distribute, I have N1 dot this plus N1 dot that, they're both 0, so therefore that's 0. And therefore N1 is perpendicular to X minus P as desired. Make sense?
Yeah, I was first trying to do the things in parentheses. I didn't know you could separate them. Like you can distribute the N1.
Yeah, it's one of these really useful algebraic properties of dot product. Yeah, you can distribute dot products. Absolutely. Yep. Okay, so now let's see. Next thing, explain how you know that x minus p is perpendicular to both v and n1. Well, we know it's perpendicular. We just showed it was perpendicular to n1.
Yep.
Right? Now let's see. How do we know that x minus p is perpendicular to v? Well, x minus p by being the closest point, I mean, x minus p has got to be perpendicular. V is parallel to the line. This is perpendicular to the line, so therefore v and x minus p have to be perpendicular. So both of these vectors are perpendicular to x minus p. Sorry?
Is there a geometric proof, like, because I never knew, like, the phrase saying that the point closest to p.
Yeah, I'm just appealing to your geometric intuition there. That if you I mean, think about it this way. Let's suppose you have this is just a tangential thing. Here's a line, and here's a point. And let's suppose you look at a point like that where this is not a right angle. Right? Well, since that's not a right angle, then what do you suppose happens as you move in that direction along the line? Well, as you move in that direction along the line, you're going to be getting closer to that point. So this can't be the closest point. Yeah, it's just kind of a little geometric. I mean, yeah.
I wouldn't have seen that. That's the thing.
I see. Well, yeah, no, exactly. And it's another one of these things that once it's been pointed out to you, then you can say, oh, yeah, okay, that's mental note.
There's another problem I think later.
Right.
That makes the same statement.
I see.
So
Yeah.
I know this. Then
Useful. Yeah, it's a useful fact. Yeah, absolutely.
okay, sorry.
Okay, so that's right. So now we know that x minus p, in being perpendicular to both of these things, x minus p is parallel to their cross product, v cross n1. And then we're calling this n2. All right, let's see the last part of the problem here. Let me scroll a bit. Okay, let's see. Use a calculation of the n2 component of x minus x naught. Okay, well, let's think about what we just showed, by the way, on the picture. What is this n2? n2 is the cross product of v and n1. And so n2 is parallel to this x minus p. It's something like this. So that's n2. All right. Right. So let's see. We're going to use a calculation of the n2 component of x minus x naught. Okay. So this is kind of the neat idea here. That. What is x minus x naught? Well, that's that vector. Well, x minus x naught has a component in the n2 direction, and x minus x naught also has a component in the v direction, but these are perpendicular. But it's you see what I'm saying? Because this vector is kind of in this plane that everything's happening inside of. And so, in particular, the component of x minus x naught in that direction is actually this distance. It's that distance there. All right, so what we want to calculate, this d that we want to calculate, is the n2 component of x minus x naught. And the good news is x is up some point that we want to know how far it is from the line. X naught is the base point given for the line, so that's given. n2, well, v is known. Okay, that's given. That's the direction vector for the line. n1, where did n1 come from? Let's see. Well, n1 was the cross product, of v, which is known, and x minus x naught, which again known. So you can directly calculate v excuse me, you can v is known, x is known, x naught is known. These two things are known. You can compute their cross product to get n1. You can cross that with v to get n2, and this calculation then, of course, is just n2 divided by the length of n2 dot x minus x naught. So once you know n2, you can compute everything in here and compute that distance.
So it'd be a pretty big one with all this.
Yeah, it'd be a big formula altogether, and that's why I didn't like write out a single formula. But like if you have a parametric line given, and you just want to compute, for a particular single point, you just want to know, hey, I just need to know this particular distance. Then this is a process that allows you to figure it out. Yeah, and it's a long and tedious process, and I think that's why I probably removed it from the homework syllabus. But it's a good exercise.
Thanks.
Yeah, no problem.